Okay, I hope that we are live now. Welcome everyone joining online for this third edition of the DeLighted Talks, which is a series of talks that are presented by the Good Light Group in collaboration with the Daylight Academy, the International Association of Lighting Designers, the Society of Light Treatment and Biological Rhythms, and Luger Research. Today's program of the DeLighted Talks, the title is The Right Light at the Right Time, Bright Days and Bright Dark Nights. The lectures are part of UNESCO's International Day of Light 2022 event that took place last week, but still in the occasion of that event, we are organizing these lectures. And the program that we will be going through in the coming 1.5 hours is a brief introduction and welcome, which I have started right now. After this, we will have a short lecture or a 20-minute lecture by Christina Blume on bright nights, bright days, and the importance of bright days for human performance, mood, and sleep. And then Koosje Lamers will continue with a lecture on the importance of dark nights for the environment and for human well-being. And we'll, after this, we'll have a panel discussion where we also will take questions relating to the presentations that are given. And in that panel discussion, also Carla Wilkins from the International Association of Lighting Designers will join. And if you have any questions relating to the lectures, I propose that to delay those questions to the panel discussions. You can also drop them in the chat and we'll try to answer them while typing as the lectures go on, or we will address the questions orally at the end in the panel discussion, or during the panel discussion, I must say. Before I continue, it's perhaps good to also introduce myself. I'm Luc Schlangen. I'm from Eindhoven University of Technology, and I'm also active as Director of Division 6, Photobiology and Photochemistry in the International Commission on Illumination, the CIE. In the next few slides, I will briefly discuss a set of recommendations on healthy lighting that were recently published by an international group of experts as the result of a workshop that was held in Manchester and to which I also contributed. Our planet has 24-hour rhythms, that are especially visible or mainly driven by the light-dark cycle on Earth, and which has a period of exactly 24 hours. And like most mammals, humans have an internal central biological clock in the brain that allows us to anticipate and adapt to this light-dark cycle. And the rhythm of this internal clock is also visible in the 24-hour rhythms in our physiology and our behavior. And you can see that here on this. Oh, sorry, I've tried to activate the pointer here. You can see that here in this slide, a few of these rhythms are displayed. And a very important marker and signal of the key marker and signal of the biological clock is the melatonin profile, the melatonin peak, which melatonin is a hormone that marks nighttime, and it reinforces darkness-related behavior, which means for a diurnal species like humans, that melatonin is facilitating sleep initiation and sleep consolidation. And there are also physiological rhythms visible in our body temperature, in cortisol peaking in the morning. And you also in behavior, you typically see that our performance, alertness, and motivation are dropping during the night, during the period at which we are secreting melatonin. And again, they are rising and maximal during daytime. And having a proper light-dark cycle aligns this internal clock to the 24-hour rhythm, but without any light being present, our internal biological clock runs at its own speed. And this speed is not exactly 24 hours. Instead, our clock has a period which is slightly longer than 24 hours. So our internal clock is ticking a bit slower. And if the internal clock is left by itself without any entraining influence of light from its environment, our rhythm will move later by roughly a quarter every day. And that's what is displayed in this graph here. So we're staying in constant darkness across multiple days. On the first day, there will be a certain period during which we secrete melatonin and normally will try to go to sleep. And this period of melatonin secretion will move later on the second day, on the third day, as a consequence of the slightly longer than 24-hour free running period of this internal clock. And if there is light in the environment, this light is able to entrain and adjust the internal clock so that it fully runs in sync with the environmental light-dark cycle. And this process is called entrainment. And here you see an entrained biological rhythm, as opposed to the rhythm being free running without any light in the environment. Now, how does light regulate this internal clock? And for that to understand that, that's important to understand how light interacts with this melatonin peak. And this is a schematic display, which is also published in this publication, where you can look it up if you would like to see more details on it. If you have light in the evening on this evening, then this light will push the melatonin peak to a later timing, as you can see here. So during this light exposure, your melatonin peak will move to a later timing. You could also say that your clock is slowing down and is forced towards a slightly longer period due to this evening light exposure. Having morning light exposure, so light after the melatonin peak, that light will, if you would have had this light this morning, then your melatonin peak this evening would shift to an earlier timing, making that you are feeling tired and would like to go to sleep at an earlier time point this evening due to this morning light exposure. Here you see again a melatonin profile in dim light on one evening or one night, and then across, saying in dim daylight, there is no melatonin during the daytime, but then again, during the next light, there will be a second melatonin peak. And if you switch on the light during this melatonin peak, that will suppress melatonin, as is shown here in this cartoon. And this is disruptive for sleep quality and usually inhibits rapid sleep initiation and also inhibits or impairs sleep consolidation. So during this melatonin suppression, that means if that happens, then you're less well able to re-enter or maintain sleep afterwards. These cartoons are showing that daytime light can adjust the timing of the internal rhythm, that it can, and that way, by aligning this internal rhythm is shown by these melatonin profiles. It's also known that daytime light exposure can enhance the amplitude of the nocturnal melatonin secretion peak in people that receive very little daytime light exposure. And also daytime light can help to improve sleep quality at night. And it's also known that daytime light exposure can alleviate at least some forms of depression. And some of these mechanisms are thought to operate through the biological clock, but there are also mechanisms that do not need to run via the biological clock, by which light could directly act on mood regulation in the brain, centers in the brain. Now, a healthy internal clock, as we will see and discuss later on in these lectures, requires bright days and dim nights. And it's good to realize that our typical electrical lighting environments results in much dimmer days and much brighter nights as compared to the light exposure that we would receive if we would have stayed outdoors all time. And here you see a nice example of light exposure measured in a group of people that were camping outdoors and only exposing themselves to natural light, so without any access to electrical light, as opposed to having the same group of people living in an urban built environment with lots of construction and being inside the buildings and as well as outdoors, being exposed to electrical light. And then you see that in such a built environment, people are receiving less daytime light exposure, but in the evenings they're exposed to more light and also at a later timing as compared to the natural light-dark cycle outdoors. And if you look, the light exposure that we receive outdoors differs in both in spectrum as well as in the amount of light that we receive outdoors is totally different as compared to the amount of light that we receive indoors. And these are two measurements. One is a measurement that I did in front of our university building here in Eindhoven on a cloudy day. And this one is the measurement below is an electric light environment within a building, pretty far from a window. So there's hardly any daylight being present. And this is almost only electrical lighting, giving rise to this spectrum as measured. And how do we now quantify the amount of light? We're using a weighting function that describes the brightness perception of humans, the luminous sensation, and we multiply that function with the spectrum as measured. Then you get an area which defines the illuminance. And in this case, you can see that the daytime lighting outdoors has an illuminance of 4,000 lux on a cloudy day, whereas the illuminance indoors, far from a window, is only 500 lux. So that's much, much lower. So just as a recap, how do we quantify light? Is again the same spectrum, as I showed on a previous slide for electric lighting, but now on a bigger scale. Here we have the photopic weighting function, the V-lambda weighting function, and that characterizes, you could say, the brightness perception of humans in terms of vision. And if you multiply this measured spectrum with the photopic weighting function, you get an area, and you could say this is the photopically weighted irradiance. And if you multiply this area with the proper weighting constant, you obtain the illuminance, which, as I've shown on the previous slide as well, is for this particular inside our university building. We have a typical horizontal illuminance far from a window of about 500 lux on a desk. And if you want to characterize the lighting for non-visual responses, it's important to realize that in the most practically relevant situations, those responses are strongly driven by a melanopsin-based receptor, which has a dedicated or different photosensitivity, and is as compared to the V-lambda function. And this melanopsin-based photosensitivity of these photoreceptor is shown here in this dotted line. And this novel photoreceptor, by the way, is called the intrinsically photosensitive retinal ganglion cell, but perhaps it's not important to recall the name. If you want to know more details, you can look them up in these publications. But it's good to realize that if you want to characterize the brightness for human non-visual responses, we should not be using the photopic weighting function, but instead we should be using the sensitivity of this melanopsin photoreceptor, melanopsin-based photoreceptor, which is characterized by this melanopic weighting function that is also standardized in an international standard. And if you then use this melanopsin weighting function to weight the spectrum, you get a quantity, this area here. If you take that full integral of that area, you have the melanopic irradiance. And if you then multiply this melanopic irradiance with the proper normalization constant, you obtain a quantity that is referred to as melanopic equivalent daylight illuminance, which characterizes the extent to which this light spectrum activates the melanopic photoreceptor within the retina. And as you can see, in this case, the melanopic equivalent daylight illuminance is only 302 lux. And if you take the ratio of this melanopic EDI over the illuminance, you get a quantity which is called the melanopic daylight efficacy ratio, which can also be considered to represent a kind of an MP ratio similar to an SP ratio, scotopic to photopic ratio, that perhaps some of you are familiar in using in your daily activities. Now, this metric, this melanopic equivalent daylight illuminance, is the metric that was adopted in a set of recommendations that were defined within a group of international experts during a workshop held in Manchester. The workshop was chaired by Tim Brown and Ken Wright. And here you see the participants. So it's a group of international experts in the field of circadian and neurophysiological photometry. And these recommendations were recently published in March of this year, so in PLOS Biology. And the title of the paper was Recommendations for Daytime, Evening and Nighttime Indoor Light Exposures to Best Support Physiology, Sleep and Wakefulness in Healthy Adults. Now, what are these recommendations based on? One important pillar is that during that workshop, we discussed a general dose-response relationship if light is quantified in terms of this melanopic equivalent daylight illuminance. And if you will do that for the response with respect to the amount of light, this amount of light being able to suppress melatonin, or to induce this phase shifting of this melatonin peak, or to drive to enhance alertness, you can see that if you increase the amount of light, that then there is a stronger response on melatonin suppression, a stronger phase shifting effect, and a stronger alerting effect of night. And that relates to light exposures that typically are more than 2 hours of duration, occur during the evening and night without any pharmacological pupil dilation being applied. And also the light exposures concern primarily broadband light. So if you look at this generalized dose-response relationship, you can identify different regions where you could say, well, these are regions that we would like to make sure that we are at least with our light exposure during different times of day within those different regions. And here, that's exactly what the recommendations of the workshop are based on. The idea was that during daytime, it's good to try to be in light conditions as much as possible that are maximally stimulating the melatonin with respect to the circadian system as judged from melatonin suppression and circadian phase shifting. And for that, you would want to be in this yellow area, which means that you typically need exposures that exceed 250 lux melanopic equivalent daylight illuminance. And this then is measured at the eye position, usually in the vertical plane at 1.2 meter height. So it's when seated, but it corresponds to the habitual viewing direction of the user. During the evening, it's good to try to have light exposures that have a minimal disruptive influence on the circadian physiology as judged by melatonin suppression and phase shifting. And therefore, it's good to try to reduce the light exposure to levels below or of 10 lux melanopic equivalent daylight illuminance or even below. And during nighttime, it's even good during the sleep period, in the sleep environment, it's good to try to have light exposures that are totally inactive with respect to their effects on the circadian system. And therefore, it's recommended to try to achieve a melanopic equivalent daylight illuminance of less than 1 lux. And only if people need to go to have certain activities or should go to the bathroom, for instance, perhaps you can switch on the light, but then try to use as little light as possible and stick below the evening threshold, but use as little light as possible during nighttime. And typically here you see the three, for typical habitual bedtime of about 11 in the evening. These are the 3 evening hours where people are recommended to stay have a melanopic equivalent daylight illuminance below 10 lux. During nighttime, have a melanopic equivalent daylight illuminance below 1 lux. And during daytime, have a melanopic equivalent daylight illuminance above 250 lux. Now, if you look at these recommendations, if you would translate them into a corresponding illuminance for different light sources, you see that the amount of light that you can still accept at night depends on the spectral composition of the source. If the source is relatively rich in short wavelength light, like typically daylight, in this case we say that is melanopic daylight equivalent efficacy ratio equals 1, then these recommendations translate to having more than 250 lux during daytime of in illuminance of a source that produces a spectrum that is exactly identical as daylight D65. If you have a spectrum of a LED source that is roughly 3,800 kelvins, or typical LED spectrum like I had shown before in our university building, then the melanopic daylight efficacy ratio is slightly lower, which means that you need a higher illuminance to achieve this melanopic EDI threshold of 250 lux. And if you go to an LED that has a spectrum which is even less rich in short wavelengths, then you even need a still higher illuminance of light before you have achieved this melanopic equivalent daylight illuminance of 250 lux. During the evening, the reverse applies. Then you can see that with still 24 lux of this light, you still are able to be below this melanopic EDI threshold of 10 lux. So this allows you to have a reasonable, slightly better visual performance as compared to having this light at night, where you could only use 10 photopic lux, and then you would already have reached the melanopic EDI threshold. And the same applies to the nighttime. Well, that is in a nutshell the recommendations. They are intended for healthy adults aged 18 to 55 years, and special considerations may apply for specific populations like shift workers, elderly, and children. And the recommendation also not meant to supersede existing guidelines relating to visual comfort, safety, and function.